This presentation covers the principle and control strategy for managing thermal state in the blast furnace, a key to stable and efficient operation. Thermal control is critical. It dictates the coke use, hot metal chemistry, and furnace stability. Excessive heat damages refractory, while insufficient heat risk chilling and hanging. Stability improves the productivity and extend the furnace life. The key thermal zone includes the raceway where the raft is critical, the posh for the reduction, the cohesive zone vital for performance, and hearth for the molten metal and slag. RAFT or Raceway Adiabatic Flame Temperature is a calculated indicator from the blast parameters. Its trend predicts the thermal intensity and is a leading indicator for silicon changes. Now, hot metal silicon is the primary thermal signal. High silicon indicate overheating, low silicon signal a cool furnace. A stable silicon within 4 0.5% makes a good control. So for rising silicon, first check the gas utilization. If stable, reduce auxiliary fuels in steps. Monitor top gas temperature. Use small wind increase cautiously and allow 4 to 6 hours for a full response. For falling silicon, priority is to prevent hanging. If top gas is high, adjust the O to coke ratio. Increase auxiliary fuel moderately. Review the blast parameters and burden distribution. But for all, you need to give a your standard thermal rule time. Slag basicity affect the thermal stability. Higher basicity increase melting point. Lower basicity improve fluidity. A stable window for basicity and magnesium oxide support both desulfurization and the thermal control. Top gas temperature is a key diagnostic. High temperature may indicate a cold burden, low temperature can mean excessive heat loss. Correlate it with the pressure drop to find what is the root cause. Primary blast levers are wind volume and oxygen. Make changes in a small staggered step. Oxygen enrichment finely tune raft. Avoid simultaneous large adjustment to prevent shocks and complications. Auxiliary fuel like PCI is a primary thermal lever. Changes should be balanced across all tier to avoid hotspot. Monitor silicon and top gas response over several hours. Plus, moisture offers fine, slow acting control. Increasing moisture cools the furnace, decreasing it provides gentle heating. It's useful for long term trend adjustment. Body distribution is crucial for thermal balance. Uneven distribution creates hot and cold zones. Modern bellows top allows precise control for better thermal consistency, and in order to combat the total effect, things are to be utilized fully. The cohesive zone position is a thermal indicator. A high position signal a cool Bosch. A low position indicate a hot Bosch. The ideal is a stable middle zone controlled by the O to coke balance. As far the hearth management is concerned, it involves monitoring thermocouples. A stable thermal profile promote protective skull formation, maintain deadman permeability, and control hot metal temperatures. Thermal cycling or frequent silicon swing accelerate refractory wear. Consistent control and smooth raft changes can extend campaign life by 2 to 3 years. Use an integrated data-driven approach. Monitor multiple signals simultaneously like silicon, RAFT, and top gas. Use moving averages to filter noise and always document action and outcomes for better results. Level 2 model provides guidance, mass and heat balance models, predict responses. Empirical model and alarm system help flag issues and suggest corrective actions. Avoid common pitfalls. Don't overcorrect a single data point. Never ignore gas utilization. Avoid making large simultaneous changes to multiple parameters, as these create instability and confusion also. A standard operating procedure is essential. Target silicon between 0.45 to 0.55 and point uh, uh, even in a unexpected situation goes to zero point 0.6. Use primary, secondary and tertiary levers in sequence and allow 4 to 6 hours for the response. The benefits are significant: 10 to 15% fuel saving, more consistent hot metal, extended refractory life, fewer operational upset, and improve downstream steelmaking efficiencies. Implementation occurs in phases. Assess the baseline, define targets, integrate model and alarm, train operators, pilot on one furnace, then refine and extend to other furnace. Now, in summary, thermal excellence require integrated monitoring, disciplined and staggered control actions, and continuous learning. A stable thermal state is the foundation for efficient, reliable, and long lasting blast furnace operation.